Hi, I'm Sierra Bergen, and today we'll be going over how a computer works. Now, it is my hope today to cover over a specific part of this section, which is the logic gates and logic circuits, which are how we get our input and outputs. Now, as we already know, the CPU is the brain of the computer. It has all of these things like the control unit, arithmetic logic unit, input-output devices, and memory units, and they're all interconnected to do something, namely process data. Now, what's going on here is when you and I input something into the computer, that's actually human language and the computer doesn't understand that. So it actually has to translate it to machine language or binary to do these processes, and then when it outputs, it will translate it back to human language again. Now, what's going on here when that happens is Boolean algebra. Now, that's exactly like our regular algebra. You and I will add, subtract, multiply, and divide, and the computer will do the same thing, but with a series of zeros, ones, and there's only three operations that happen when this process goes on. The AND operation, which is to multiply two inputs together, the OR operation, which is to add two inputs together, and the NOT operation, which will invert the result of whatever the input is. Now, like regular algebra, there is an order of precedence to this where not has to be considered first and will be considered next, and then or will be of the least importance when doing these operations. And the reason this is important is because, as you can see by my diagrams over here, a logic gate is simply that, is a pictorial representation of electricity moving through the computer to do these operations. Now, as we said, the NOT gate will take an input like A and invert it. The AND gate will look at two different inputs and compare them, and only when both are equal to 1 will it produce a result of 1. OR takes two inputs, compares them, and when at least one of them is 1, it will produce a result of 1, or otherwise it will be 0. And we have an exclusive OR, which is similar to an OR, but where OR says that as long as there is 1, 1, there will be a result of 1. Exclusive OR says there has to be only 1 to produce a result of 1, otherwise the result is 0. Now you'll notice here that I also have a NAND gate, a NOR gate, and an exclusive NOR gate. And they are a combination of the NOT gate and whatever other logic gate is here. And so they will do the same thing as their AND, OR, and exclusive OR gates, but produce the opposite results. So NAND, where normally 1 is produced, will produce 0. NOR will produce 0 when 1 is normally produced, and exclusive NOR will also produce 0 when 1 is normally produced, and vice versa for all of these. Now, why are these important? Well, because they are a major part of the logic circuits, and when information is being passed through, you have to have input be compared in order to produce a certain result. There are two kinds of logic circuits, speaking of which: a combinational logic circuit, which doesn't require previous data, it only requires the input and the logic gate to produce some kind of result, and a sequential logic circuit. These require an input, an output, sometimes previous because it may need to interact with the registers, and an actual time factor such as a clock. So what is going to happen is that at a certain time, the electricity will go through a sequential logic circuit, and it will produce a result based on the information that is already there. And so I say that for a sequential logic circuit, but in reality, both of these logic circuits require an active low or high signal, meaning a 0 or low voltage needs to be produced, or a 1 or high voltage needs to be produced in order for a result to happen. Now, the way I think of these to distinguish them is I think of a TV remote example. On a TV remote, you have two different ways you can change a channel. You can simply input some random number and it'll change the channel. You do not need to know what the previous channel was to change to this channel. That's a combinational logic circuit. Whereas the sequential logic circuit is more like that channel up and down button. The TV needs to know that it's channel 3 if you want it to move to channel 4 or down to channel 2. Now, I have two examples here, the first being a combinational logic circuit known as a ripple carry logic circuit. This is what the arithmetic logic unit does when it's, for example, adding two numbers. In this case, I have 4 full adders, which consist of two logic gates. So in my case, I have a couple of exclusive OR gates, and it compares 3 outputs to produce, not outputs, I apologize, inputs, 3 inputs to produce 2 outputs. Now, when you and I add in regular algebra, we compare two numbers and we start from the rightmost number and go over to the left. It's the same in Boolean algebra. Now, because we are starting from the rightmost digit, our carry will always be 0. And so essentially what this will be doing is it's saying, okay, compare these two values, which will produce a 0, and now compare it to the carry. Because a carry was not created by comparing these two values, we can have a sum of 0 after comparing all of the inputs, and a carry output of 0, which now ripples over or takes that carry flag into the next bit, which will now be 1 and 1. And when we compare these, they produce a result of 0, but a carry of 1, and so now our carry output is 1, our sum is 0, and it will continue to add these, so it'll compare these, produce 0, but a sum of 1, because now we have to take into account this carry flag or carry value. Produces a sum of 1, a carry 0, until the function is complete. So in this case, when our output is 0, 1, 0, 0, or 4. And that's essentially what the arithmetic logic unit does. This is one way that it could accomplish that. Through a series of gates and circuitry and whatnot, it produces a result based on inputs. That's it. And so the other logic circuit is the sequential, or for example, I have a set reset latch or an SR latch. Now, as we can see here, we have outputs that are already established. This is what's known as the set state, what we're starting off with. This is our channel 3, so to speak. Now, as we can see here, this appears to be a active high signal kind of latch. And so what's going to happen is I have this set state here. Now, when I apply a high signal or high voltage to R, what's actually going to do is it's going to channel this 1 through. It's also going to produce a result of, our result's still going to be 1 because it has nothing to compare in our NOR gate to. It's going to follow down and actually become part of the comparison for our S gate or our set gate. And now what it's going to do is it's going to compare our 0 and 1, which normally in a OR instance produce the value of 1, but because it's NOR, produces the opposite. Now sends out a 0 signal to the Q and will now compare. This will be a 1 compared to a 1, which will produce a 0, but because of the NOR, it now produces a 1 result. And that would reset the latch. The opposite can be said about the set operation. Instead of resetting to whatever default state, you are now going to set it to a new state where your results will be opposite. And so something like this will be used for connecting to registers and setting certain states in those registers, such as setting data to an address, for example. Now, speaking of registers themselves are small bits of fast data. And, for example, things like program instructions are handled here. And so what the computer does is it says, okay, I have these instructions, do this thing. And so when you're running a program on a computer, how this is handled. The CPU says, all right, control unit, I need you to go do something. Okay, and the control unit goes, fantastic. Hey, save data, where something like a paint program is stored. I need to get a copy of all the instructions for a paint program, and it's going to send those up to things like RAM, RAM registers. It's going to say, okay, here's all the instructions. I've created a temporary copy of these, and what I need you to do is, while someone is interacting with this paint program, execute those instructions. So, create the color green. Okay, now draw something in the color green. And it's going to do that until an interrupt action is executed. In other words, closing the program. And once that is done, it actually clears out those registers to make room for something else, say like, oh, I don't know, a PowerPoint presentation to run. And the fun thing with registers is you can actually have sub-registers within these registers. For something like, oh, say I'm running a PowerPoint and I decide I want to pull up a paint program. What that's now going to do is the CPU is going to say, hey, I need you to go in now. You're going to go in, grab paint instructions, put them in one register, grab PowerPoint, put it in another register, and we're going to be able to run these simultaneously until execution programs are run for each. And that's essentially how a computer works. All it really is the computer is sending electrical signals, It's doing some kind of Boolean algebra through logic gates and logic circuits, and it's producing results based on the input that is provided. These are the sources that I used to gather all this information, and hopefully I was able to help you understand how a computer runs just a little bit better. And thank you for watching.